Thanks for the introduction. My name is Roberto Montano. I'm a PhD at Interact Lab from the University of Sussex in the UK. And I'm going to present NaviFields, which is a working collaboration with the University of Castilla-La Mancha. Virtual reality navigation is often constrained by small volumes. For instance, the boundaries in the interaction space, such as the chaperone in the video. This is a well-known problem. A simple solution is by using scaling factors. For example, in this scenario, we are scaling the user displacement for a scaling factor of 6, allowing the user to reach the entire environment and creating the illusion of navigation in bigger spaces. But the problem is when the tasks that require more precision are needed. This could be a challenge because the scaling factor also affects this precision movement, which is not good. We propose NaviFields, which is a navigation technique that allows designers to define relevant locations into the virtual reality scenarios. As you can see here, the positions that require more precision and interaction are defined. For example, control panels, computers, some boxes maybe, and next to the door to take cover and see if someone is coming for the corridor. And then we apply the scaling factors in non-relevant areas, allowing navigate faster across those spaces. Then, when the user approaches to a relevant position in the scenario, this scaling factor is gradually decreased, allowing more natural interaction in precision tasks. But how does NaviField work? Once the highly relevant points were defined in those positions where the precision movements were needed, which represent the 1-to-1 movement ratio, such as the natural interaction, we compute the relevance of each point in the field, creating a continuous field which controls the displacement gained in the virtual environment based on those relevant computations. This creates a compression effect of the non-relevant areas in the field, while at the same time allowing users still interact in a natural way into the relevant ones. But how those transitioning areas around the interested locations are working on? Well, when the user is navigating across these relevant areas, the scaling factors is set to 1, so as the same as natural interaction. But whenever the user is going through these transitioning spaces, the user displacement and speed are linearly increased in order to reach the outer scaling factors. We include these transitional spaces because we wanted to avoid this suddenly jump from natural interaction and a scaling factor of 4 or 6, for example. This could be quite disorienting. But what happened if we have an overlapping of those transitioning spaces, as we saw in the video? So in that case, the behavior of the first transitional space is going to be something like this, pretty similar than the previous example. And the behavior of the second transitioning area could be the inverse, because we are gradually decreasing these scaling factors in order to reach the 1-to-1 movement ratio in the highly relevant zone. But now we have this overlapping section when we have 2 values for each point into this path. How can we solve this? Basically, taking the lowest value in each of those points, making sure that we have a smooth transition going out of the first transitioning area and into the next one in order to reach the next target. Of course, we wanted to test if NaviFields is a suitable navigation technique for VR versus natural navigation, which is the best kind of navigation that we can have so far. And we expect a lot of differences here in this comparison. But we wanted to know if these differences will come from the fact that NaviField breaks this 1-to-1 mapping, or from the fact that NaviField has an exocentric control technique, which means that not all the control in the speed and displacement is based on user movements. One example of this is that if the user is going across the non-relevant areas, the scaling factors is going to increase in order to make the user move faster across these non-relevant areas and reach the next target faster as well. Then we include an additional technique, which is homogeneous scaling, which also breaks this 1-to-1 mapping but keeps the control in the user at the same than natural navigation. For our user study, we wanted to take into account this navigation paradigm in VR, which can be defined as three simple tasks. The first one is a target search. Basically, decide where do we want to go. Then, the physical displacement, which is called traveling. And at the end of the traveling, sometimes the high precision tasks are needed. This is called maneuvering. And then if we want to continue navigating, we can follow the recipe, just look up for the target, travel to the target, and do a kind of precision task. One example of this is probably align the eyes with the lenses in the microscope or adjust the focus. Sometimes that may require high precision in the movements. For our user study, we keep these three simple tasks, but to be honest, there is not too much that we can evaluate in target search because the user is going to go where the user needs to go. So we keep only two tasks, and we create a two-step task for our experiment, traveling and maneuvering. In this case, this is an example of how this experiment looks like. This is the first part in traveling. You can see in the middle of the screen the scaling factor embedded in the environment. This is changing according to the position of the user in going to this environment. And whenever the user reaches the final one, this is the maneuvering task, and the user needs to align their eyes and orientate the gaze in order to finish this task. Well, let's talk more in detail about these two-step tasks. And the first one is traveling, and we are using 6 flags where the user needs to go through some semi-randomized path. If you want to know more about this semi-randomization, please refer to the paper. There is a nice explanation there. And, of course, we wanted to assess task completion time starting from the point that the user reached the first flag and finishing the point where the user reached the final one. We are also evaluating the real travel distance, which is the distance in the real world when the user goes through along this path. And, of course, the virtual travel distance, which is the same as the previous one, but in the virtual space. And also, we wanted to measure the deviation from the best path, which is, could be represented as a straight line between the targets along each specific task, path. Sorry. In the second step, we reuse the parafrustum technique, which takes into account 2 main variables. First, the head size, which is represented for these 2 spheres there, where the user needs to align their eyes, as you saw in the video. And we are allowing some tolerances here. So plus minus 1.5 and 3 centimeters in tolerances. And once the user is in the correct position, needs to align their gaze and orientate the gaze towards the center of the flag. And this is also called tail size. We are also allowing some tolerances here, plus minus 5 and 10 degrees. And also, we wanted to assess the effect of the posture in this maneuvering task. And we are assessing the standing posture, the medium, and the kneeling down. And of course, we also measure the task completion time, starting since the user start aligning the eyes, positioning and orientation errors, and the number of attempts that the user took along this task. And at the end of each trial, we include 4 basic questions, because we wanted to know how easy or how comfortable was each traveling and maneuvering independently. For the factorial design, we include 3 scaling factors, 2, 4, and 8. And just imagine that you have a real available space of 2 by 2, and if you want to use a scaling factor of 2, you will interact with a virtual environment of 4 by 4. In the case that the scaling factor is 4, you will interact with the virtual environment of 8 by 8, and so on. We also took into account 2 path lengths, 3 and 5, which represent the number of flags that the user needs to visit along each path. And of course, we also took into account two techniques, NaviFields and homogeneous scaling in Latin square randomization. And at the end of these 12 blocks, we had a final block, which is the natural navigation. We are considering this natural navigation as our baseline, and the results that I'm going to present in the next session are presented as a deviation from this baseline, because we wanted to know how good or how worse the behavior of each of our techniques are compared with this baseline condition, the natural navigation. The results in traveling okay. The results in traveling show some interesting things that I'm show you in a second. There, right there. Okay, NaviFields compared with homogeneous scaling showed lowers deviation from the best path, and we found significant differences in all scaling conditions. And if we compare NaviFields versus natural interaction, we found significant differences only in the scaling condition of 8, which is good. In real travel distance, we found significant differences in the scaling condition of 4 and 8. That is true in the case that NaviField is affected for longer paths because we are using natural areas that we are not scaling at all in those areas, so NaviField is affected for these longer paths. But even if the user needs to travel longer paths by using NaviFields, we found no significant differences in task completion time, which is quite good because that means that the user actually travels faster when using our technique compared with homogeneous scaling. And also, the user is showing more confidence when using our navigation technique. In terms of comfort and easiness in interaction, NaviField was rated as a more comfortable and easier than homogeneous scaling in almost all conditions. Now let's take a look about the results in maneuvering. In terms of task completion time and the number of attempts, we found significant differences in all conditions if we compare NaviFields versus homogeneous scaling. But the interesting thing here is that if we compare NaviFields versus natural interaction, we found no significant differences in any condition tested in this experiment. That means that NaviFields behaves like natural interaction when we are in this maneuvering task, in high precision tasks. But we found another interesting thing, that the effect of the posture in these high precision tasks, for example, kneeling down had the worst performance in almost all variables tested in this experiment. That could be explained maybe because of when the user adopt this kneeling position, the displacement is a bit towards in front of the user. This could fall outside of the relevant area, so it's a bit difficult to actually adjust. In comfort and easiness, we found no significant effect just in the scaling factor of 2, which is quite interesting because this can suggest that users can adapt their movement to finally control their gaze and posture in scaling factors up to 2. This is also supported by the results in positioning error and orientation error, that we found no significant differences also in this scaling factor condition. As a conclusion, NaviFields, we present NaviFields as a VR navigation technique that computes the relevance of each point in the virtual environment and scales the user motions accordingly. We provide a mathematical characterization of the technique and implemented it for a testbed environment, compared NaviFields' performance for traveling and maneuvering. And our results shows that NaviFields is a suitable technique to navigate and interact within the virtual environment and also provide insightful information about the interaction in VR, such as the case of the effect of the posture and how much scaling factors the users can actually tolerate when navigating in these precision tasks. That's all for my part, and thank you very much.
In that case, I'm going to ask a question. And it seems to me that there's an elephant in the room, and it's kind of like in Dumbo the Elephant, the Disney cartoon. It's a drunken elephant swaying from side to side, which is VR sickness. You're changing the relationship between what my eyes see and what my inner ear tells me as I'm moving around in the environment. And so can you say something about the effects on your users wearing these commercial head-worn displays in terms of VR sickness or cyber sickness?
I'm sorry, can you repeat the question?
The question is about VR sickness or cyber sickness.
Oh.
Right, and what effects does this have on your users? Because you are mismatching between what your inner ear tells you and what your eyes are telling you in a very major way, including acceleration.
Yeah, of course there are a lot of variables that we can test in this kind of experiments, but the motion sickness was not one of those that we test here, unfortunately. But yes, of course, there are some people really that can be really affected for this kind of motion. But a good thing is that we couldn't find too much people in our experiment that was affected for this motion sickness.
Interesting. Anybody else?
Hi, I'm Junyab Lee from KAI, South Korea. Also, following up on Professor Fina's question, it seems that because you have different velocity gains in certain regions, say if you're constantly accelerating in that region, it seems to me that there would be like a third derivative. So that would amount to a jerk, velocity acceleration jerk. And it seems to me that in your experiment, the users found, in some cases, the scale factor of 2 more comforting than homogeneous acceleration. Could it be that the jerk played a part in maybe making users feel more comfortable?
In the case, you're referring to how much the user can compensate this scaling factor up to 2, or I couldn't. Oh, sorry.
Anybody else? Okay. In that case, boy, this is going to go by a little faster than we thought because our next speaker is already standing at the podium. He managed to quickly